If you've been wanting to learn more about the VG diagram and how that applies to you as either a pilot going through upset prevention and recovery training or as an instructor, you've come to the right spot because that's exactly what we're going to talk about today. Hi, everybody. My name is Paul B.J. Ransbury. I am the CEO of Aviation Performance Solutions. It's just a wonderful opportunity we have here today to get together and talk about a really critical topic, which is the VG diagram use in upset prevention recovery training. And I have a great group of experts here with me today, and I'd like to go ahead and introduce them. Right to get going, I'd like to introduce at the bottom Captain Clark McNeese. He's our VP Standards here at Aviation Performance Solutions. Clark comes from a background flying in the military. He was an F-18 fighter pilot in the U.S. Navy, went from there into the airlines where he spent nearly 10 years as an airline captain on the Boeing 737. And he joined us, Otter, probably 18 years ago now to lead our program here in upset prevention and recovery training. And he oversees standards, customer experience, just an all-around great guy, a good friend. So Otter, welcome. And why don't you say a few words and introduce our very special guest today?
Yeah, thanks, BJ. It's great to be here with everybody and talking about one of my favorite topics, UPRT, and even the VG diagram specifically, because it's actually one of my favorite tools to use in UPRT. I'm excited to be here with Dave once again, Captain Dave, as I call him. Super guy. You know, Dave has been with us for a lot of years as well. He is our currently our Boeing type specific UPRT expert, and he helps keeps us straight as we say as we go through working with the various airlines and customers that use the Boeing aircraft. There, Dave comes from a long history, certainly of flying over 40 years. After surviving Air Force Academy, went on to serve in the Air Force, flew T-38s, T-37s, F-15s, even the C-141 as well, instructed numerous times, and then on to 29 years at Boeing, where he was served as chief pilot of technical and safety for the test and evaluation, flew all the models, was current in them all the way to his last flight, which I even got to see in the 747. Was it, which model 747 was that, Dave, that you actually did your last flight on?
That's a Dash 8 freighter.
Dash 8 freighter. It was a beautiful airplane.
Yes,
but it was. But he's been with us ever since, and it's great to have him back on. Now, Dave is no small potatoes, shall we say, in the UPRT world, because he is actually one of the original authors of the Airplane Upset Recovery Training Aid. He and especially Larry Rockcliffe of Airbus. But Dave has been an industry leader and mover and shaker in this area of training for a lot of years. Was on the ICATI group of the Royal Aeronautical Society, and I served with him on the stall stick pusher working group there for writing Advisory Circular 120-109. And so anyway, he's just comes from vast experience and has helped us in the industry to lay out standards, best practices, and guidance material in the delivery of UPRT, because it's one of those fields. It's one of those areas where we've had a lot of cooks in the kitchen, and unfortunately, we haven't been doing it right all the time either. And we've got several accidents that we can call on because UPRT was not conducted properly. Dave, it's great to have you again.
Yep, I'm glad to be here, Otter.
So, Otter, I think Dave was going to outline a situation that he had faced there that was related to a VG diagram understanding or would have benefited him. And I think you were going to hold back the thunder till the end of the presentation. Is that right? Did you guys want to have that discussion before we get going?
Yeah, no, I think this would be fun for him to share his story. As I communicated with him a little while back, getting in preparation for this webinar, he literally had just come out of this incident that he encountered in his airplane. And I'm going to let him just tell kind of the facts of the story here and what happened. And then a little bit later, we're going to relate his story to the actual VG diagram itself. So, Dave, you want to talk about what happened?
Yeah, the story is pretty simple. I was having some interior work done on my airplane that was finished, so I was going to go up flying. I decided I'd invite a friend of mine to fly with me who was a former military pilot, spent the last 30 years flying commercial. So obviously he did aerobatics and stuff like that when he was a military pilot. But as we'll find out, UPRT experience is fragile and perishable. We went up flying in my RB6, and I asked him, I let him do quite a bit of flying. I asked him if he would want to try a barrel roll, and he said sure, and he started into the maneuver, and I tried to talk him into getting the nose a little bit higher and to increasing the roll rate, but unfortunately for us, we ended up in a barrel dive, and so we were extremely nose low and accelerating and pretty fast, and I hated to take the airplane away from a 22,000 hour pilot, but he just didn't have the small airplane UPRT experience. And so I took the airplane and started right in on the APS recovery. And so when I pushed and I rolled, and then when I went to do my reduced power, I happened to look at the airspeed, and it was accelerating rapidly and was very close to BNE already. And I didn't know exactly how low I was, but we were over the hills here, and I was very nose low, and ground was rushing up quite quickly. I don't think it was a imminent ground impact, but was definitely required an aggressive maneuver at that point to pull up. So did you want to stop there, Otter, and then we'll talk about the VG diagram?
Yeah, I think what I want you to relay here, right here, just at this point, and we'll talk about the VG diagram a little bit later, but you actually made a concerted decision as to whether you should over G the airplane or let it overspeed. In other words, not pull as much G, but let it overspeed. And
That's correct.
You made a decision on that.
That's correct, Otter. As we'll see in the VG diagram for commercial airplanes, there's a 2.5 G limit. And so we don't expect commercial pilots to have a 2.5 G butt and be able to figure it out, right? So we tell them to use the same rotation rate that you have for takeoff, 3 or 4 degrees per second. And that gets you roughly around 2 Gs in most environments. So it's relatively aggressive. Now the RB6 has around a 6 G limit, but I don't know what 6 Gs is all the time. But I do know from over the top maneuvers what about 3 or 4 Gs feels like. And so that's what I started to pull up. I knew at that very high speed with the ground coming up at me, I did not want to snatch the G in because I would overstress the airplane or pull off the wings. So what I did, knowing the VG diagram, I accepted an aggressive G level, but not to the maximum because I wouldn't know what the maximum was. and I accepted an overspeed condition because I know from VG that there's some margin built into that. And for example, when I flew commercially, we had a margin, what we called VD or V dive. And so that was roughly 50 knots more than VMO. And then at high altitude, maximum Mach, MMO, we would have to take, for example, 747 out to 0.97 Mach. So 10 or 15% margin in that. So I accepted, like you said, I accepted the overspeed margin in order not to over-G the airplane.
Gotcha.
Great. Well, that's wonderful, Dave. And we'll have a chance to look at the VD and the margin there a little bit later in the transport category diagram. So that's a great preview. And I just want to mention all the people joining us from around the world here today. We have all the way from France, the UK, we have Brazil, Hong Kong, even Kentucky in the United States. So we got people from all over the place. So it's just wonderful. So let's go ahead and get started here and start talking about the VG diagram, guys. And I'll just take us through it, and I'll kind of go to you to add color and comments as we go. We'd like to try to wrap up the kind of academic presentation of this around the 45-minute mark, if we could. But again, if it's good discussion, we'll just keep going. But we would like to get to a few questions today, and I think all of us can stay for as long as there's questions. So if the folks out there have any questions, please go ahead and post them into the chat. We have Carrie Bryson with us on the channel, that she is our Director of Marketing and Communication. She'll be helping with some links and resources as we move forward. Now, one thing I wanted to mention here is that the VG diagram represents one part of a larger picture that we call the UPRT cognitive map. And you can see it's a circle starting at the very top. And the very top part is called the persistent threat of loss of control. Pilots generally don't understand the magnitude of the threat of loss of control and how it exists in the current paradigm. And in fact, the current paradigm of training is exactly why it exists. So to get perspective on that, but you'll notice as we move to the right, the very first course before we start the subsequent 9 courses is a deep understanding of the advanced VG diagram. Now, for everybody here on the presentation today, we have what's called our free UPRT Insights course at no charge, which provides a high-level overview of all of these courses to give you a good general understanding of what this cognitive map looks like. And Carrie's going to go ahead and post that link into this stream here so you can get access to that free course as being part of the event with us today. But we're going to focus on the advanced VG diagram. Now, if you want, there's an in-depth program in that, an hour-and-a-half study that you can decide to pursue if you like. But today we're going to be focusing on that particular side of this knowledge base, which really is the foundation of everything else. So this diagram right here is what we call a VG diagram. So if you're a typical pilot, you may have seen this, you may have learned to answer a couple of questions on it, and then probably largely blew it off after that as part of your training as a pilot, because we have a tendency to live in a very narrow margin on this curve, which we're going to get to a little bit later. But this is truly something that tells you the limits in so many different areas, from speed to G to angle of attack, and different features that you need to understand. So let me just briefly talk about what the diagram is, and then I'm going to have Otter talk about how a picture's worth 1,000 words here in just a second. So on the left side, we can see the G loading, and that actually is telegraphed by the name of the diagram called the VG or the VN. G and N refer to the load factor, and then V refers to the speed along the bottom axis. So looking at this diagram, there's a couple of things that give it away to me that I know it's a general aviation airplane. One, the airspeeds in general are kind of general aviation airspeeds, but most importantly, we take a look at that center blue box, is what we call the normal operating range. We're going to talk a little bit more about what normal really means in a minute, but its positive limit load factor is 3.8 G. Now, the airplane that Dave talked about a minute ago probably had a plus G and -3 load limit on it, so the diagram would look different for it. And as we'll see later, the upper limit on a transport category airplane in a clean configuration is 2.5. So if we look to the bottom of the blue block, we're starting to see the negative G limit at around 1.5 G. And off to the right, we're starting to see the airspeed limitations. And that red area is a region of structural damage or failure. It can be caused by airspeed, airflow, pressures, flutter at the top and bottom on stressing of the airplane. but this is just an important diagram for us to understand as pilots. So Otter, that's kind of an overview of what we're looking at. Do you want to maybe just give your commentary on why a picture is worth 1,000 words to you?
Well, I think this is a great diagram to help pilots visualize better where they are, not only in the normal envelope, but also as we go through and learn about the various upsets. Because this diagram is really best used in a dynamic format. It's designed to be used to plot where you are in the diagram, shall we say, second by second throughout either the upset or the recovery itself. And it allows you to see where you are, whether you're in the heart of the envelope or whether you're at the edge there. A lot of people call that dark blue area the normal envelope. I'm not a super fan of that there, because you can see, for instance, this normal category airplane here is certified to go to negative 1.4 Gs there. And even though the airplane can, by certification, can actually go to negative Gs, aerodynamically and structurally, I tell you, there is nothing normal about being in negative Gs. So, but I think one way of thinking about this dark blue area is it's the non-stalled and non-structurally damaging part of the flight envelope.
Right. And we're going to talk about that a little bit later in a future slide, where we actually break this up in more of a practical layers so that you as pilots can understand how to better understand where you're at in this envelope. So actually, right at the beginning here, let's go ahead and get Carrie to post that link to the VG Advanced Applications course if anybody wants it. Okay, let's start looking at some of the speeds here. And then we're going to compare this to a transport category diagram later. So off to the far right is what Dave alluded to earlier, V&E, which varies with airplane. And then we have this very interesting one that is at the intercept of the lift limit and the upper load limit, called maneuvering speed. Now, to clarify what I mean by lift limit, if you look at the upper left and the bottom left of the diagram, you will see what's called a stall region. And what separates the stall region from the normal envelope, or even the region of structural damage, is that white upper curved line right there. And you can see it right along the top. And what that is a representation of this particular airplane as the critical angle of attack. So in other words, from a pure physics standpoint, it is not possible for this airplane to be at 80 knots and 3G. Just can't get there. The wing can't generate that level of performance. But all along this curve actually represents your stall speed at all the airspeeds associated with the bottom. Now, we can tell by looking at this diagram that either this is an asymmetric clean wing or any wing that has a flap selection, because we can see that the curve of the upper area has a different shape than the bottom one. So an airplane that has a symmetric wing, for example, it would look the same or similar top and bottom. So the VG, or the maneuvering speed, is the minimum airspeed at which you can apply maximum G, or maximum available G. Now, the thing to remember from a practical standpoint as pilots is that when we are to the right of maneuvering speed, the threat is overstressing the airplane, structural damage, by getting over aggressive on the elevator. When we are now on the left side of maneuvering speed, if we get aggressive by burying the elevator or pulling back, we will be now running into the stall. So risks on both sides of it. The point is, to the left of VA, you're lift limited. To the right of VAE, you're load limited. So the next speed that we have here is something we should all be familiar with. And sure enough, this is the 1G stall speed. How do I know that? Is because it's the intersection of the 1G line on that lift limit, that upper white curve. And if we drop down to the speed area, you'll see that is 65 knots. So that is a very typical understanding of the VG diagram. And very often you're limited to just those questions when you're going through your certification as to where these are. So Otter, do you maybe want to talk about what the pilots experience day in, day out by living on the 1G line? And I got a few arrows I'll bring up that'll start at the left at zero airspeed, then take us up to cruise at about 200 knots. Do you want to talk through that?
Yeah. So, we pull out on the runway, and there we are sitting at 1G at zero airspeed. And he's got that little arrow there that shows that. 0 airspeed 1G. And now we add the power. We start accelerating down the runway. We're getting faster and faster. And eventually we'll get to our rotation speed. We'll pass, of course, pass our 1G stall speed. We've got to get a little bit faster than that, obviously, to rotate. But we'll rotate and then usually begin to climb out at some initial climb speed. Maybe in this case, it might be 90 to 100 knots, might be your cruise climb speed or something there, as displayed by this red arrow on the right. And then once you get up to cruise altitude, you'll usually accelerate and then accelerate to your cruise speed. In a prop airplane, it might be around this region, maybe that fast, maybe not. In a jet, you're probably going to be a little closer to the right, a little closer to your VMO or MMO, just from a performance standpoint. But eventually you descend, and then you get down to your approach, and you slow back down to your approach speed. And then eventually we touch down and add the brakes and come to a stop. So we operate in a pretty small portion of the VG diagram, right along that 1G line typically.
Absolutely. So we're within a small fraction of that in most operations. Even flight training, all the way up to 45 degrees of bank, is a fairly narrow margin on that. And often we don't completely understand what's going on there. So let's go ahead now and kind of focus in on a situation. Let's talk about a practical application of how the VG diagram can help us understand our limits and shape what we would do in certain situations. Let's just expand into this area and take a look at this region. And let's say now that we're on approach at 90 knots, Otter, and I think this would be a discussion. Why don't you jump in there and take this forward for us? So we're now in our general aviation airplane that's represented here. We're on approach at 90 knots. That's the appropriate speed. We don't want to be faster because of stabilized approach criteria. We don't want to be slower because of stall margin away from the 1G stall. And there we are. Why don't you take us through a scenario that could be useful to everybody on the event here today?
To do that, now one of the questions I like to ask pilots at this point, just to make sure they understand how to read the diagram, and that is, all right, guys, here we are in this airplane at 90 knots, and I'll say, all right, can we do a 60-degree angle of bank level turn? Can we do a 60-degree angle of bank level turn at 90 knots in this airplane? A lot of guys will look at it and then I'll have to remind, all right, now how many G's do we need to pull in order to do a 60-degree angle bank level turn? And we got to pull 2 G's. Now let's look at the diagram here. Can we pull 2 G's in this airplane at 90 knots? And we can see we cannot. In fact, if I were to roll into my 60-degree angle of bank and then begin to pull back on the elevator so that I get my 2 G's, we go vertically up the VG diagram as we increase G load, and I would hit about 1.5 to 1.6 G's, and then we would exceed critical angle of attack, and we would stall. And that would be called an accelerated stall. We would never even make it to 2 G's there if I attempted to do that steep turn at that speed. Now, it's usually at this point that I like to say, now, does everybody understand why wake turbulence is so dangerous? Because visualize now being on approach in this airplane at 90 knots. And now you fly through a rolling vortex, some type of rolling vortex. And the airplane does an uncommanded roll to a 60-degree bank angle that you can't stop. Now, once that airplane gets to that 60-degree bank angle, where do you think the nose of the airplane is going to want to go? Yeah, it's going to want to go down. And what's going to be your gut reaction to that nose drop on approach low to the ground? It's going to be to hold the nose up, and you'll pull the airplane right into an accelerated stall and aggravate the problem. And you see, you can't react that way. That's it. You can't do that in that scenario. We're going to have to actually do something that's counterintuitive in that scenario. But I think the VG diagram really helps us to see the margin or lack of margin of safety that we have when we're in slow speed flight. like on approach, and having to deal with some type of upset like that, and being susceptible to our gut reactions and how we could aggravate our upset as well.
So I think it right here on the diagram here, Otter, it talks about unloading the airplane, and that's counterintuitive. In fact, the push or the unload is going to be a theme of what we talk about here in the event today. There's just so much information on the VG diagram, but probably the biggest skill set that is lacking to pilots, especially in a crisis, is the technique of unloading, because pilots are generally programmed to load or pull. And unloading requires a push. And we're going to talk about later that pushing isn't necessarily negative G. In fact, with proper training, it's an unload to a light positive G. In fact, you can see the blue arrow here now unloads down to about a half G in this particular example. Now, in that situation that Otter talked about, have to accept the nose drop, right? Have to accept the airplane's nose drop, unload the airplane, reattach the airflow, reorient the lift vector so it's working against gravity, and then we can start bringing the nose up. But when we unload in that situation, there's a couple things going on. First off, we're reattaching the airflow. Secondly, what's happening is we're minimizing the dive angle, because it's going to optimize our roll rate to get the wings back underneath us. And if we start getting really fast, we're also unloading because of asymmetric load on the airplane, which is something we're going to talk about a little bit later. So this is a great example, I think, Otter, that takes that accelerated stall situation that people feel like they could never get into and puts it into a practical scenario. Dave, anything you want to add to that at all in this particular example of a general aviation airplane on approach at 90 knots?
Yeah, if you really think about it, if you get a stall situation, you're on that curve up there, and the very first thing that you got to do is to push and move down the chart to half G type environment. And you can see at a half G, the stall speed drops down to about 40 knots. And so, yeah, it's really important that if you do get to that stall line, to unload the airplane and be able to maneuver the airplane from there.
Great. Okay, guys, I think that's a good discussion on that. Anything else to add? Time to move on? Okay. All right, let's talk a little bit about some key relationships. So for the instructors on the call and even pilots in training, there are some fundamental relationships, and we're going to show 6 of them. I want to talk about the first 4 first. On the VG diagram, we've talked about the load and unload margins. So for example, up to the positive G, down to the negative G. We're going to discuss that in a little bit more detail. Speed margins left and right. We move left to the stall, as we've demonstrated already. We can also move all the way to the right for overspeed or high speed limits of the airplane. So diagram represents, guess what we've talked about, the labels. Remember, it's a VG diagram. So yes, it gives you the margins and safety limits on load and unload, and speeds left and right at the stall and high speed. But some other things that are very interesting is that the shape of the VG diagram can change for a lot of different reasons. For the weight, your altitude, the configuration of the airplane as well can affect the shape of it. For example, if we configure an airplane going from clean to a selection of flap, that upper white curve, that lift limit curve shifts up and to the left. So in some respects, it expands your available envelope, but it also typically caps the amount of load available. So going from, for example, in a transport category airplane, goes from a 2.5 G limit down to a 2 G limit, and then completely removes the negative G envelope from -1 down to 0. So while we gain some margin when we configure the airplane, especially in the slow speed environment, we now start affecting other features. And the VG diagram is excellent at showing that. The last one I want to talk about is really the dynamic relationships that we've been telegraphing here in our conversation, is how stall speed is related to the load of the airplane. So a good example of that is somebody asks you what your stall speed is. Very often you're just going to repeat exactly what the 1G stall speed. Probably a better answer would be, under what load are you referring to? Because your stall speed can be at any airspeed all the way up to maneuvering speed. And it's important to understand that as a pilot, that we as the pilots control our margin of safety away from the stall. And we're going to talk about that in a second. There's a couple more I want to come back to a little bit later. Otter, anything you want to add on these key relationships that we can extract from the VG diagram once we're fully trained on understanding it?
No, I think it's good. Just again, I'll probably iterate that from an aerodynamic standpoint, kind of all of us pilots understand that our heavy airplane has higher stall speeds than when we're lightweight. And basically that is the same aerodynamically from a load standpoint, pulling G's. Same thing, when you increase G load, AOA goes up, drag goes up, stall speed goes up.
Exactly. So people often ask, well, how does weight possibly change the shape of the curve when it's actually a load curve? Well, you can just think of it more as your weight changes, the interception of the 1G line intercepts a different part of the white curve that gives you a different stall speed as you start loading the airplane. Okay, anything to add here, Dave, on these key relationships?
Nope.
Okay, all right. Big thing to remember here as we move forward, as you understand the envelope of the airplane, the envelope being speed limits, G limits, angle of attack limits, is that it has a huge impact on your awareness, not just in upset prevention and recovery training, but translates to your everyday operation of your airplane to understand where you are and what your margins are, and a good understanding that you control those margins of the pilot, largely based on what you're doing on the control column for angle of attack and load, and also what you're doing with your energy and drag devices on left and right on the curve. Okay, all right, so huge impact on awareness. Okay, let's go ahead and jump into this diagram here. And now what we're going to do, Otter, is we're going to go ahead and change this and I think bring the layers in that you were talking about. And since you brought it up, I'm going to get you to talk to them. Why do we make the diagram look like this? Why is it more useful to pilots to think of the VG diagram like this?
Well, I've seen that this really does help pilots to visualize what part of the VG diagram or what part of our flight envelope is good, shall we say, and bad that we want to stay out of throughout an upset recovery. Now, if you look at this, there's the 0G line. And below the 0G line, it's red, and that means negative G's. Now, negative G's, even though the airplane is certified to do it, typically in most airplanes, we don't want to go to negative G's in an upset recovery because now we'll talk about maybe killing the fuel pumps or hydraulic pumps. If you got passengers, especially if they're not strapped in, now they're going to start hitting the overhead there. So avoiding the negative G part of the flight envelope would be very important and would be a key goal in building a competency in upset recovery. Now, the 1G line, of course, is the separation between the light green and the blue that you see there, and that's where we typically operate. But that light green area represents the unload zone, and it's the light positive G. There, the airplane is still positive in G's, meaning fuel pumps, hydraulic pumps, that kind of thing are still working. People are still sitting in their seat. They're just light in their seat, and you're light in your seat as the pilot. But it is an appropriate area to go. And as we see in good UPRT, you show why unloading the airplane is so beneficial in so many upsets. There, but this is a perfectly acceptable place or part of the flight envelope to go. Unfortunately, most pilots have little to no training in how to actually unload the airplane into that zone. And I've put pilots there myself, flying along an airplane, and I don't tell them what G load I'm going to do, and I'll just unload the airplane to half of a G, pretty much right where your little cursor is right there, BJ. That's half of a G. 0.5 G's is what you would see on a G meter. And I'll ask most pilots, hey, what G load are we? And most pilots will say it's either 0 or negative G's. And just in case there's a terminology concern, I'll ask them, well, let me ask you this. Would you ever unload your Citation jet to this? And they'd say no. Would you ever unload your 737 to this? And they'd say no, because it's too much. There. And so anyway, it just goes to show that I think we're missing a major area in our flight training of teaching pilots how to unload. And these colors help us to be able to visualize where those zones are.
And I think
Yeah, the negative G portion is actually for commercial type transports is a very difficult place to get to. It's a lot more than you might think in order to get it down to that environment, and it's a very difficult point in flight testing to achieve. So yeah, it's very difficult to get down there.
Cool. That's great. And so one thing maybe to just translate here, Otter, is there's a big misconception out in the industry, especially in simulator training, which of course you can't experience unload in the simulator, certainly not accurately, not beyond a very initial brief portion of a second. But the thing would be that in airplane upset events, the vast majority of airplane upset events, pushing is often the right first step. And the vast majority of those, or a large portion of those, unloading to a half G is often the target you are going to. And both of those are foreign to pilots in the way they're trained in the current paradigm. And so one of the things that I would say, Otter, is that generally speaking, do you feel that whenever you talk about pushing, people think that means negative G? Anything you want to clarify there at all?
There's a little bit of a terminology misconception, I think, for some pilots, and that is some pilots think that anything less than 1G is actually negative Gs. But that's, as you can see, that's not really the case. When you feel less than 1G, when you're light in your seat, you are still positive G, but you are not negative yet. Now, you know when you're negative G's in an airplane by the fact that you are now out of your seat and you're up against your straps, your coffee and your iPad have hit the overhead, right? Now you know you have overpushed.
Yeah. Except for an extremely unlikely situation, it is highly unlikely, if not ever, you're going to go to a negative G as the appropriate technique in an airplane upset event. And one thing I always talk about is the fact, Otter, if you do go to negative G inadvertently, how tight are your straps? Where are you going to go? You're going to go out of your seat. How do you sit down again? You grab the controls and try to pull yourself into the seat, which is exactly the opposite of what the situation is demanding for survival. Okay, guys, I think we did a great job in here. So let's talk about the use of elevator, the push and pull. What's that look like on the diagram? So if you look at the white arrow, the arrow going up is the pull or the load, and the arrow going down is the push or the unload. And that has a huge impact on the stall speed. Take a look at the interception of that upper arrow on the white curve. That stall speed in that situation is 120 knots. But by pushing and unloading, we can see that the stall speed nearly instantaneously goes from 120 down to 40. So the great news, even though big airplanes have a lot of inertia, there's time for it to respond. You have fairly immediate control over your margin of safety away from the stall and how you unload airplanes. So the thing, and the reason why this is an important topic and why we're talking about the push so much is that of all the fatal loss of control in flight accidents, nearly 50% are associated with the stall. And very often it's due to pilots not understanding that they are stalled or how to get out of the stall, and the fact that they can control their margin pretty readily, if not immediately, especially in smaller airplanes, to get there. So the big message today is the push and the unload gains you margin of safety away from the stall in one example. It does other things as well, like optimizing roll rate, eliminating asymmetric loading. There's other reasons to push, but the point here is to try to ingrain that moving away from the upper area of the VG diagram is generally the right first step that we are going to do in an airplane upset. Now, that said, there's always exceptions, right? Okay, so real quick, how important is angle of attack in airplane upset events? So this is another course we talk about, which is the 6 essentials in all upset recoveries that essentially communicates that in every airplane upset event, there are 6 things that have to be addressed by the pilot, and typically in a proper order to approach it. So if you take a look to the circle on the right, you can see within the context of type-specific considerations for your model of airplane, whether it's general aviation, a glider, a 737, or an Airbus, in the context of your knowledge of your airplane, the very first place you land often is addressing angle of attack as the first priority. In fact, I think it's fair to say, and I'm going to go to Otter and Dave here in a second, in many situations, and a stall is a great example of an out-of-control condition, if you don't effectively manage angle of attack as one of the first steps, very often the rest of the steps either don't matter or can't be accomplished, depending on what's going on. So Otter, do you want to talk about that briefly before we move into transport category VG diagram?
Yeah, I mean, a cross-controlled stall is a great example of an airplane in an upset. In this case, an aggravated stall where you are stalled, but the airplane is also rolling. And most pilots are very attitude sensitive, and if there is some type of uncommanded roll going on, we're going to typically try to fix it right away. Just don't even think about it. Naturally, put in counter ailerons. And if you were to do that as a gut reaction to that uncommanded roll without having solved angle of attack, you're at risk of aggravating the problem and potentially even putting the airplane in a spin.
Dave, any comments of the important role of angle of attack here in the context of upset recovery?
Yeah, the fact is that you could be in an upset, and if you're pulling too many G's, your roll control will basically evaporate. And US Air 427 is a great example of that. They got in a very high bank angle, nose down, a lot of G pulled, and so they lost roll control. And in that case, you have to unload the airplane in order to unstall the wing so that you get that roll control back.
Excellent. That's a very, very good point. And we're going to see that a little bit later when we start talking about, for example, recovery from an overbank high G spiral or an overbank nose low. And I just want to let everybody know that we're seeing the questions coming in. Thank you. This is a great time to put them in there. We'll be getting to those at the end of getting through the academic training part of the presentation. Okay, folks, here's a transport category diagram. All right, so a little bit more complex. A few more lines going on, but at the end of the day, it's essentially communicating similar or the same concepts. So there's the 1G line. So yes, transport category airline pilots live along that 1G line. That's where it is in this representation. Over on the right now, we can see that VMO is now analogous to VNE, but to Dave's point, if you move to the right of that, you can start seeing VD, which is the overspeed region. If we look to the top of this diagram, you can see your upper load limit of 2.5 G. That's a clean configuration. If you configured it, it'd go down to 2 G. And the bottom limit is a negative load limit, -1. Remember, general aviation was down at -1.5, 1.52. And again, this is clean. If you configure this airplane, typically it's going to go to a 0 G limit. And then there are those characteristic lift limit curves, top and bottom of this wing. So hopefully that translates the general aviation concepts into this diagram. It's just a little bit busier. We wanted to make sure that it's clear as to what this diagram means. Okay, so we're going to clean it up again. Anything you guys want to add to that, Dave and Otter?
Yeah, like in my RB6 situation, when you go into an overspeed region in a commercial aircraft, the hatch line area there, the test pilots have to fly all the way out to BD and determine that the airplane is fully maneuverable and recoverable back into the normal envelope with normal piloting skills. So if you get in an overspeed situation due to wind change or something like that, you're 3 or 4 knots fast over BMO. Don't get excited about that. Just pull the power back and slow down. It's nothing to be excited about. We go well past that when we test, and it's not a concern for the safety of the flight.
Great. Thank you, Dave. Otter, anything to add to this from a clarity standpoint?
Yep.
All right. Okay. Let's jump in here and just do a few examples, guys. Remember the theme of the conversation today, and remember there's a lot of things we can talk about in the VG diagram, but given the scope of what we're doing and the time, we're going to largely focus on angle of attack management. We'll quickly address some of the other features when that's relevant. Let's talk about the typical kind of 1G ab initio stall or typical type rating recurrent training stall experience. And if you remember recently in the past 10 years or so, there's been a re-emphasis in stall recovery that the primary focus is angle of attack management. It's not minimizing altitude loss. We want to start with angle of attack. And when we get to the stall, just remember in your mind, when you think stall, approach to stall or stall, the first thing that should enter your mind is not maintaining pitch and adding power. It's to reduce and manage angle of attack that's telegraphed by that blue arrow right there. Otter, anything you want to add to the kind of vanilla traditional stall considerations on the VG diagram?
No, you pretty much said it there. And this is why it's so beneficial to see this in relationship to our normal stalls that we practice, because it helps pilots visualize the benefit of immediately unloading and not worried about power, not worried about even speed, but just the immediate unload and what that does for your margin.
Awesome. Absolutely. Okay. Let's move on to an accelerated stall, because that kind of is analogous, although the speeds would be different. The load is different in this particular case, is that now we move up the curve a little bit. And so in this particular situation, lift limited in this scenario. But here's an example of where our textbook clean VS speed, our stall speed, very quickly goes to a different speed. And we can see here that it's a much higher speed. Same thing, we want to reattach the airflow by unloading the airplane. And very often this occurs in a circle to land approach, over aggressive with the airplane, maneuvering at high altitude with inappropriate bank angle. This can appear for a number of reasons from an accelerated stall standpoint, but the characteristic push to reattach the airflow is critical. Dave, anything you want to add on the accelerated stall in this particular position on the curve from a pilot experience and knowledge standpoint?
Yeah, most pilots are used to the fact if they're pulling too hard and all of a sudden you get the buffet of an accelerated stall to unload. It's a natural reaction. And the VG diagram shows exactly what happens when you do that. So yeah, you gotta push.
Immediately generates margin of safety, and so there is no reason for a stall to be an ongoing threat. It should be immediately mitigated by the pilot by reducing angle of attack, and no matter what your flight attitude is, reducing angle of attack is a forward movement from your reference frame in the cockpit to reattach the airflow. Otter, anything to add there, or maybe I caught you in a yawn?
No, that was actually what you just said is important, because this is what we see, especially if you've entered an accelerated stall in a nose low type of attitude, or even slightly nose low, and you're low to the ground. You're not gonna want to unload because you see dirt over the nose or altitude losing. So it is a way for us to see that we've got to go forward with the elevator. Going forward with the elevator is how you unload an airplane, no matter what the attitude is, even nose low.
Very important point. Thank you. Let's jump on to this nose high upset. Now, this is an interesting one that people don't often think about. Now, how would you ever end up at a nose high upset intercepting that curve up at the top and requiring a push? Well, one of the things to consider here, and I'll let you guys talk about a little bit more. Here we have the United Airline model with the old paint scheme on it. Just love it. Is what we're going to be in a situation now, for whatever reason, runaway trim, pilot distraction, and maneuvering for traffic, maneuvering for terrain, the airplane gets to a nose high flight attitude. And depending on the thrust setting, depending on the altitude, this can be a situation of very rapid decrease in airspeed in this particular airplane. And very quickly, and we're going to take a look at how quickly things happen in the VG diagram a little bit later with a video of a UPRT IOS. But in this situation, very often pilots don't realize that the imminent threat is actually the nose high stall. And so the nose high stall is approaching very, very quickly. So we are moving rapidly to the left on the VG diagram. And if we ever get close to or touch the upper lift limit, we have to unload. And take a look at that blue arrow. It looks like it's an over push, but in reality, getting to a half G is critical because your airspeed is winding down like crazy. And depending on the airplane and recommended technique by the OEM, it may just be a complete straight wings level push, or in certain situations, you may have to unload all the way full forward and then actually roll the airplane to help roll that lift vector off to get the nose coming down. But it's not uncommon in these scenarios, especially anything 30 or 40 degrees nose up, to be over the top of that below the 1G stall speed, but there's no reason for the pilot not to be in full control. And they have to push and unload below 1G to be there, which is a great example of why in your mind as a pilot in an upset, including a nose high unstalled upset, is managing angle of attack, even though you're not stalled, is you're mitigating the threat, which is the upcoming stall if you don't manage angle of attack effectively. So, Dave, why don't we go to you on this, on the nose high upset? Anything to add on there to transport category or any pilots in this scenario?
Yeah, I think it's important to understand the thrust impact for a nose high thing like that. Those underwing mounted engines, and you add a lot of power, it's just going to push the nose up and cause the airplane to slow down even faster. So the thrust effect for that nose high situation is a big deal for commercial airplanes.
Absolutely, yeah, and it's starting to counter the push, right? And I think that in smaller airplanes, the thing to remember is very often pilots think that in a nose high upset, it's speed deterioration is the number one threat. While that is true in one sense, remember airspeed in a nose high upset event really just helps you control the airplane, assuming that your angle of attack is below critical. All right, so it maintains energy and controllability, but what's really keeping you safe is the unload or reduction of angle of attack to take advantage of that energy addition or reduction, depending on the situation, like Dave talked about, to maintain controllability. Otter, anything to add there at all?
Nope.
Okay. All right. Let's jump into one that's perhaps a little bit more, not necessarily complicated, but there's a few more things going on. And this is one of the harder areas to teach in upset prevention and recovery training, because nearly every element of those 6 essentials in every airplane upset needs to be looked at. Well, in this particular situation, let's start with a spiral. So this is a scenario. So very quickly, I know our time's ticking away on it, and we want to get to questions. So the airplane gets overbanked, the nose starts dropping, and you're relatively high on the speed curve. And instead of getting into the accelerated stall that we talked about earlier on approach, is we now start pulling to try to stop the nose drop. The airplane starts overbanking, and now we're trying to use G to get the nose up. And one thing to remember is in a transport category airplane, when you're above that critical bank angle of 66 degrees, there is no amount of G within the limit load of the airplane to get the nose back up to the horizon. We have to now start with fundamental principles. And again, in the context of type-specific considerations, the place to start here is pushing, but it's not to get out of the stall, it's to stop pulling, right? So it's making it worse by pulling. So we want to unload. How much you unload is going to largely depend on how steep you are. Not a bad practice to think about targeting back down to the unload region, because remember, in this scenario, especially at high airspeed, you want to start unloading, managing energy and drag, and you want to start rolling the airplane. So there's 3 values of unloading in an overbank, especially at high airspeed. First off, by unloading, you're stopping your contribution to the nose drop. Remember, we have gravity and lift is turning the airplane at least 2G. Here, if we're truly at 3G, it's a 4G nose low turn to the ground. We want to unload the airplane. At this airspeed, we want to eliminate asymmetric loading, especially in an airplane with big wing-mounted engines. And remember, being unloading, because of what Dave talked about earlier, it's going to optimize your roll rate to get those wings back underneath you quickly. Because if you're successful by unloading and rolling, remember, by unloading and rolling property, you're going to minimize your airspeed gain. You're going to minimize your dive angle, all of which count towards minimizing your turn radius, which is altitude loss. And of course, managing energy based on where you are in relation to maneuvering speed is critical in this. So that's a lot of things said there, a very short period of time. But Otter, anything you want to add to that? I know that it's not fully comprehensive, but that's as quick as I could go to cover the key items.
No, it is a lot of information. And then again, this is, I think, what a good UPRT program is going to help pilots to understand is how this fits, how this all relates together dynamically, and the practical training really makes it come alive.
Awesome. And then, of course, I want to bring up the slower speed one for the same situation. And the point of this is, in fact, we have an animation coming up where the pilot is very much closer to that new blue arrow, that second blue arrow. And in this particular scenario, yes, instead of the load limit being the threat, the stall could be the threat in an overbank if you're at lower airspeed like a wake turtle's encounter. But fundamentally, the principle of recovery is transferable and largely the same. And it's important to understand those 6 factors that we listed earlier to be addressed typically in a standardized order to help mitigate a wide diversity of situations. Okay, guys, anything to add on that? Dave, I went through a lot of stuff, and Otter added some color. What did we miss?
No.
Okay. All right, let's move on now to our video. We don't ever have a presentation without a video. I'm looking at the time. We're almost there, folks. Thank you for being patient on the questions. I want to talk about at least two latter ones because now we've been largely talking about the academic understanding of the VG diagram, but I can tell you, especially in an airplane upset, your position in the VG diagram is anything but static. Now, in your day-to-day operation, living on the 1G line, it largely is fairly controlled and slow, but in an airplane upset, it changes fast. So dynamic movement inside the VG envelope is really important to understand, and understand what's happening when you apply your recovery techniques and what you are doing from a margin of safety and limitation standpoint. And very often when we're looking at a improved instructor operating station, which we're going to show here in a minute, you can actually see startle response. You can see rapid movement of flight controls by spikes in the up and down. Remember, push and pull was largely a vertical movement on the VG diagram. You can very quickly sense and see as an instructor some startle indications based on what you're looking at. Now, a lot of information without seeing a picture. So the last item at the bottom is the National Simulator Program, ICAO, and the FAA 121 air carriers now with 121-423 extended envelope training are requiring improved instructor operating stations, of which one of the diagrams that's included is the VG diagram. And so that's really important to understand that it's part of a bigger picture, but understanding your limits is absolutely critical. There's other diagrams, alpha, beta plot, control position we're going to show. But the idea behind that VG diagram, or the instructor operating station overall, is to allow less experienced instructors to provide higher quality training with a deeper, more clear insight as to what's going on in the event. All right. So impact on awareness, absolutely. Let's now take a look at an ILS, guys. And I'm going to go relatively quickly through this because we're running out of time and I want to get to the question. So here's a screenshot of an ILS station from a CAE simulator. I like it. The bottom part is just presets. Let's kind of ignore that for the purpose of this conversation. If you take a look to the top, it's hard to see here. When we go to the video, it's going to be clearer. We're going to zoom in on it. You can see now what's called the 4 plot. And if you look to the top right, you can see diagram representation. And what it does is it plots your position on the VD diagram, typically at 1 hertz or one item per second. And what that allows the pilot to see is what is the trend of the maneuver based on when recording is started and how they got to where they're going in the next representation at 1 hertz every second. Now, the top left one really quick is an alpha beta plot. The alpha beta plot essentially represents the fidelity of the maneuver that was being conducted. In other words, did the simulator accurately or fairly represent what the real airplane would have done? And it will show the instructor, was that maneuver conducted within flight test data? Was it conducted within wind tunnel data, extrapolated data? The further it gets away from flight test data, the less certain the instructor can be that the simulator correctly represented what the airplane does, but it's still representative. It's just a matter of understanding the fidelity of the simulator. Very often people wonder why the airplane doesn't behave the way the simulator that works. That's not really the way to look at it, right? The simulator is a best guess as to what the airplane's going to do. You can also see down on the bottom side of that upper screen, control position, throttle setting, trim configuration, then the bottom right, and we're going to move to the video. The bottom right now is the primary flight display so the instructor can see what the pilots flying are looking at. Okay, what we're going to do now is we're actually going to go to an animation of that last scenario that we just talked about. An overbanked nose low. The airplane's nose pitches up. It gets overbanked for whatever reason. Pilot distraction, disorientation, the nose starts dropping, and the pilot initiates a recovery. There's a few things they do well and a couple things that they don't do well, but the important part of this video is I want you to see how dynamic the movement is in an airplane upset. And so that you can actually see that your understanding from an academic standpoint in studying one plot, it truly needs an in-depth fluency of an understanding of VG diagram to truly know where you're at in the flight envelope. And again, just not in airplane upsets, but in your day-to-day operation. Let's go to the animation and I'll talk through it briefly. It's only 20 seconds long, but look how much the airplane's position and the envelope maneuvers during that time. Here we go. So there's the VG plot up top. Take a look at the bottom right. You can see the flight out of the airplane getting overbanked. The airplane pilot now unloads, but take a look at the top right. He goes to negative G in an overpush because he's in a sim, gets the wing back underneath him. He's accelerating, looking at the movement to the right on the curve, bringing the nose back up and getting him stabilized. And folks, that is 15 seconds, now 20 seconds on this video. Look at that spanning of the envelope in that particular situation. So we as pilots, while this is an academic process, what we need to realize is that our ability to understand what's going on in real time truly requires a fluency in the understanding of the VG diagram. So Otter, let me get over to you and Dave for any comments to add here. And I'm going to go take a look for questions for us to answer, okay? Anything you want to add?
No, I'm looking forward to the questions. I can see a number of them here, and it's going to be fun to touch on these. Dave, I know this is a fun topic for you as well to talk about. You're very experienced at using the VG diagram even as well, and a lot of the UPRT you were doing. Did you find out, do you agree as well that it was a beneficial tool?
Oh, absolutely. It gives you understanding of where you are and why things happen the way they do. In other words, say, for example, you get stalled and you push. You can see your stall margin go right up, and the VG diagram is very explanatory of why that happens.
It's great.
Okay, guys, here's a great question. Okay, how much difference is there in a VG diagram between a 737 and an Airbus, an A320? A follow-up question, what is one of the most important things a pilot should think about and understand when type rated on both a 737 and an Airbus?
Well, I'll take a stab at that one. That I'm not a bus driver, but the VG diagram is very similar to both those airplanes. Their envelopes are very similar. The one thing that pilots need to understand about it, that if you're type rated on both, is that the A320 is got some G limitations. So when you get to the top of that VG diagram, the airplane itself will prevent you from exceeding the top of that envelope for G. And that can be a good thing or it could be a bad thing. The good thing is that it prevents unwanted excursions and those kinds of things up there and prevents a stall. The bad thing is if you really need that extra G to avoid a collision or a ground collision, you're not going to be able to get there. So it's kind of a trade-off.
Yeah, and having flown the Airbus for a number of years, is that it's the flight envelope protections that helps keep you within the envelope are substantial. And they're all available in normal law, but as you start degrading to alternate law in an A320 or alternate 1, alternate 2 in a 330 or a 340, they start deteriorating, and it's important for pilots to understand what goes away and what they keep. And into direct law, it's very much like flying a conventional Boeing airplane. But at the end of the day, it just need to understand some protections are there, but they're not always there depending on the situation. Go ahead, Dave. Sorry.
Yeah, there's a very good incident, 757 up in the Scandinavian area that had an incident or an upset where they ended up very nose low, 20 flaps, and they ended up pulling 4.3 Gs on the 757, and they rounded out about 200 AGL, and they recovered, and the airplane was actually fairly not undamaged. But if it was a envelope protected airplane, they wouldn't have been able to make the corner down there. So it's just a trade-off, BJ.
Great. Thank you, Dave. I talk a little bit here. I'm going to pull up a diagram here that I don't know if it's going to help. Dave, this question is a good one, talking about gust limits, probably referencing to maneuvering limitations in relation to maneuvering speed, because gust limits have a different trajectory. Even though it's not marked on here, you will see, folks, this diagram actually shows the changing upper limits in a configuration going from 2.5 down to 2. It shows the shape change configuration of that upper shift and lower shift. But Dave, do you want to talk about where the gust limits overlap and how they might be represented on a VG diagram, if at all?
The gust limitations for a commercial transport category airplane are basically immaterial compared to a smaller airplane, just because of the total energy involved. The gusting factors just don't move you around the a VG diagram like it would be for a very small airplane. So basically consider the limits that you're seeing right now applicable to gusty winds or not.
Great. Thank you, guys. I'm just going to briefly pull this question up here on the Airbus. We have a great session by Captain Brad Bennett, probably the leading expert on Airbus upset prevention and recovery training. So, Dave, I'm going to point you over to that, and Carrie can send you the link to that event where we talk about Airbus recovery and considerations. It's a unique area of knowledge that may not resonate completely with everybody on the call, but I want to make sure that you have access to a resource that you need, and certainly we're happy to talk to you about that. All right, let me just move on here now. Here we go. Here's a question maybe we'll end on here today. Otter, is there any big difference between jet and turboprop aircraft? And I'm assuming it's in relation to VG diagram understanding and use.
Well, really from an aerodynamic standpoint, from a handling standpoint as well, even from a needed skill set in relationship to upset prevention and recovery, virtually no difference. Now, there's type-specific considerations, absolutely, especially as it relates to power and the wing type and all of that. But as it relates to a VG diagram, we can make a VG diagram very similar to the VG diagram for a turboprop will look very similar. It has the same kinds of lines. We only need a few data points to actually be able to draw it out there. So I think the short answer is really there is no difference.
Right. And for example, I mean, we use jets here at APS for upset training. We use pistons in our location in Dothan, Alabama for military location. Use a turboprop Grobe 120 TP. So we have a deep understanding of these airplanes. And to Otter's point, the VG diagram is a great representation of the envelope for all the reasons we talked about today in various airplanes. All right, it looks like another question just came in here. Let me just bring it up, guys. For the last year's training pilots, commercial planes are not encouraged to fly manually. What is your opinion on this fact versus UPRT? And let's end on this question. And Dave, why don't we go to you for the initial comments?
We encourage, the manufacturer encourage pilots to fly manually in order to keep their manual flight skills fresh. In other words, yes, automation is a great tool and makes it a nice ride for everybody. But to a certain extent, you got to keep up your manual flying skills for when the automation doesn't work. And so the basic guidance is if you're doing a very complicated departure, arrival, in the weather, all that stuff, yeah, sure, use the automation. If it's a nice day and you have the time and the effort, go ahead and fly a little bit manually, keep those manual flying skills sharp so when the day comes that you need them, they're there.
Otter, wrap us up with your thoughts on manual flight operation proficiency. Now, there is a new advisory circular by the FAA that gives great guidance, but I don't want to steal your thunder. Go ahead, Otter.
No, I was just wanting to say they are imploring us to. So those of us that are in leadership or management and flight departments, we've got to somehow make this a requisite for our pilots and a regular dose in some way It just helps pilots better to understand the energy of the airplane, energy management, and it's good prevention skills is what it is. Now, the great thing about sending pilots to UPRT, especially UPRT that incorporates on-aircraft training, is it contributes to their manual handling skills there. So it's a great way of building a robust set of skills, especially in this highly automated age.
Yeah, and I think the only thing I would add there is that upset prevention and recovery training, yes, is designed to mitigate airplane upsets, awareness, prevention, and recovery, but it's incredibly powerful in developing the cognitive process of manual flight operation proficiency and manual handling that is very transferable, that applies in every single day that you operate your airplane. And the VG diagram is a great example of just one element of the training that you get during UPRT to further expand your knowledge of the envelope to be safer every day. So with that, I'd like to thank everybody that is here on the call today. Just so you know, this will be immediately available as soon as we end the event for replay, and it's going to be available in perpetuity here online for you to watch anytime you want. Dave, thank you so much for being here. Always a great pleasure to have you, sir, and your deep and wide expertise in all areas of upset prevention and recovery training. And Otter, thank you for being here and giving your perspective on everything as our leading expert at APS on UPRT. So with that, folks, thank you so much. Appreciate your time. We went over time a little bit, but I think it was well worth it. Take care, everybody. Bye-bye.